parallel portion of the program is going to begin, and up to that point the parallel execution has to take place. So that is what is going to be done with this compiler directives, where the specific things and the instructions are going to be provided to the compiler so that the accordingly execution can be facilitated. And with runtime library routines and environment variables, the other subroutines and routines can be made available. So the specific thing regarding OpenMP is that it is portable, and there are number of APIs which are very much specific to C, C++, and Fortran. So you can create your OpenMP program either in C, C++, or in Fortran. And as of now, it has been implemented for most of the major platforms, including Linux platform and the Windows platform. And if you talk about what is the full form of OpenMP, then in short version, it is being said that it stands for Open Multiprocessing, and in the long version said it is the open specification for multiprocessing. Of course, in this case, the number of industry, whether it's software or hardware, government and academia are coming together to collaborate to facilitate their work. Now, the question is why we make the use of OpenMP, because it is more efficient and it is going to hide the low level detail to the programmer. And apart from that, this OpenMP directive is going to allow the programmer to specify the parallelism, and it is also going to specify whether the variables in the parallel sections are going to be private or they are going to be shared. Apart from that, it is also going to specify how exactly and if the threads are going to be synchronized. So at what place the threads are going to be communicating with each other, at what place they are going to be clubbed. So those things are going to be specified with this particular OpenMP. Apart from that, it is also going to tell us how one can going to parallelize the loops. It is also going to specify how the work is going to be divided among the number of threads. So in short, we also call it as a scheduling. So how those things are going to be done, that is going to be specified with the OpenMP directives. Now, before moving further, we must have to understand the things at the backend so that we can create the OpenMP program. So, as in the initial sessions, you would have realized, or you would have now familiar with what is a HP system and the components of HP system. So, in the HP system, you would have now know what is a node, right? So, to remind you once again, a node is nothing but a standalone computer in a box, and usually it is going to comprise of multiple CPUs, processors, and cores. It is also going to have memory and network interface cards, right? And what is a specific thing regarding nodes are that they are going to be networked together to comprise a supercomputer. So in this diagram, you can say, or you can see that in HPC cluster, we may have a number of nodes, right? And within a node, we may have number of sockets, right? And on a particular socket, we may have a processor, and inside that processor, we may have a number of computing cores. And thereafter, each and every computing core may have their own cache memory, and they can have their own. They can have their own memory, or they can even share the memory in the form of RAMs. So this is the basic setup of a node inside a cluster, and this is how an HPC cluster looks like. So as told that we are going to have a network of nodes. So some of the nodes may have a designated job. For example, in this case, these nodes are designated as a login node. So they are going to ensure the login task of any user or programmer. And apart from that, the actual job in the background is going to be carried out by these compute nodes. And as we can see, all these nodes have been connected with each other. So as a group, they can come up to solve a particular problem or to carry out a particular problem. So if we talk about the formation, so as stated earlier, that in a node we may have number of sockets, right? So as you can see in this particular case, in a node we have got two sockets. So this is how a particular chipset looks like. So these are the sockets. This is the first socket and this is the second socket. And these are the places where we install our RAM, and these are the places where we install our GPU cards, graphics card, right? And physically this is how a node look like. So we have a node, and in a node we may have number of sockets, and then in those sockets the processors are going to be installed, and within those processors we are going to have number of cores. So if we don't explicitly tell the programmer or a particular application, then they are going to make the use of these cores randomly. So more or less they are not going to utilize these core efficiently. So that is the problem. So even though if we are having a good workstation, having good configuration, and if you are running a computational intensive program, so it is not necessary that by default those programs are going to make the use of these computing cores at the same time. So if we have got a i5 processor, so more or less in general we get a quad core, right? And if we have got i7, then we get octa cores. So that means we have got 8 number of cores in that system. And if we have got 8 number of cores, then that means we can make them 8 number, we can carry out the work from all those 8 cores at a time. So that sort of multiprocessing we can carry out with that i7 system. So that is the main purpose, that if we have got a powerful machine which encompasses number of cores, so how we can ensure that all the cores are working, right? So that we can have an efficient system. So that is the purpose. So OpenMP is going to provide us that flexibility so that we can program each and every core so that all of them can be utilized efficiently. Apart from that, if we talk about the parallel programming models, so basically we have got two types of parallel programming model. The first one is, sorry, I'm getting one chat that screen is not visible. Is it so?
It's visible and also audible.
Okay, someone just stated in the chat box. Okay, thank you. So we have got a parallel programming model. So there are two types in this. The first one is shared memory model, and the second one is distributed memory model. So in the first one, we may have number of computing cores, also called as CPUs. So in this case, each and every CPU are going to have their own cache memory, and most importantly, they share a main memory together, right? So that is the characteristic of this sort of model. Whereas in case of distributed memory model, although each and every CPU has got their own cache memory, they can have their separate main memory, and they are then network. So in order to make this system efficiently, or in order to use this system efficiently, we have to go for MPI, which is message passing interface. And if you would like to carry out the work with this sort of system, then we make the use of OpenMP APIs. So in this lecture, we are going to see the use of OpenMP. Apart from that, we just try to understand again what is the difference between shared memory model and distributed memory model. So practically, if we are having a system, let's say quad core system, so in our desktop basically we may find that there are 4 cores, right? And we have a RAM. So if all the 4 cores are making or sharing this main memory, that means we are talking about UMA. And now consider a scenario where each and every CPU or the core of a system have got their own RAM. That means they are forming a NUMA system, which is NUMA, non-unified memory access. So that is the difference in between these two. Now we have got one more type, that is coma, and in this case what happens that whenever there is a large requirement or more requirement by a CPU, so dynamically that sort of memory is being provisioned to that core. So that's what happened in coma. And we have already discussed what we mean by UMA and NUMA. Now, if you talk about the differences, more differences in between UMA and NUMA, then UMA contains a single memory controller, while the NUMA may utilize several memory controllers because we have got separate memory spaces. So we may have multiple memory controllers. And now in UMA, the memory access time for each CPU is going to be same because they are going they usually they are going to have the same access time due to the length, right? Because each and every CPU are utilizing the same memory space. So that is the main reason because of which they are experiencing the same memory accessing time. While in contrast, the this thing is not going to happen in NUMA. Now, apart from that, UMA is being utilized in a variety of general purpose and time sharing application, whereas NUMA is being employed in most of the cases in real time or either in critical application. In UMA, we may have the network, the multiprocessor architecture such as single, multiple, and cross-bar buses, whereas NUMA is generally being employed in the form of hierarchical and T-structure network connections. And in the terms of bandwidth, the UMA architecture has got the limited bandwidth, whereas the NUMA generally has the higher bandwidth than the UMA. And the memory access in UMA is slow, whereas in NUMA it is going to be faster. Now, just to recall once again, the OpenMP is going to provide us the portable shared memory programming, right? And it is very popular. Why? Because it is easy to learn, and OpenMP specific commands in source codes are going to be processed by the compiler. Apart from that, the OpenMP functionality is switched on by a compiler specific options. That is also a good thing. And the parallelization is fully controlled by a programmer, and it provides us the flexibility. We can program it in Fortran or maybe in C or maybe in C++. Apart from that, it also provides us the runtime, library routines, and the environment variables that makes a programmer that provide a programmer the flexibility to program the things on the runtime as well, right? Now, the OpenMP is based upon the fork joining programming model. There are a number of programming models. So basically, OpenMP is based upon this one, which is fork joining programming model. So at this start, we generally have a master thread, and the moment the parallel region or the forking is being done, number of parallel threads are going to be created. And at the end of the parallel region, all the created threads are being destroyed. And again, the master thread is going to take the control of it. And let's say there comes another parallel region. So again, the number of threads are going to be created. And upon the completion of their job, again, they are going to get destroyed over here. And the master thread is going to take the control. So this is the basic flow of the fork join programming model. Now, the moment the forking is done, the number of threads are going to be created, and those created threads are going to be numbered from 0 to n minus 1, where n is going to be the total number of created threads. And this is a particular routine which is going to give the number of available threads. That routine is omp underscore get underscore num underscore thread. Omp get number of threads. And this routine, which is omp get thread number, is going to tell the thread and its number. So these are the two basic routines regarding the thread. Then a single program with several threads is able to handle several tasks concurrently, and apart from that, each and every thread has its own stack and register. So that is a very important point to notice. Now, so as of now, we have just understood that in OpenMP, we make the use of fork join programming model. So whenever a forking is being done, number of parallel threads are going to be created. So they are going to be number from 0 to n minus 1. So let's suppose we have got a system. Let's say we have got a octa-core system. So number of available computing cores in that system is 8. So hypothetically, we can create maximum 8 threads given the scenario that the hyper threading is not enabled. So if that is there, then at each and every core, we can create 2 threads. So as of for simplicity, we are going to assume that for each and every computing core, one dedicated thread is going to be created. So if we have got octa-core system, means if we have got 8 number of computing cores, then it makes 8 number of threads can be created, and those threads are going to be number from 0 to 7, right? Am I clear with up to this point, participants?
Yeah, I hope it's okay, sir.
Okay, thank you. So thereafter, to explain that fork join model in more detail, you can consider a program, a basic C program, where we have got a main function, right? And inside a main function, we are defining some parallel region. That means we have got a big program, and within that big program, there are certain instances where we need to make execution parallel, right? So wherever we feel that this is a portion which requires a huge computation, and this computation can be run in parallel, so over there we are going to make the use of this pragma directive. Okay, so let's say in this program there have been 2 instances. So at all those 2 instances we have made the use of this pragma directive, right? So that means at this place the parallelization has to be done, and at this place again the parallelization has to be done. So initially we will be having a master thread, right? So this is the master thread, and the moment this pragma is being encountered in the main program, so the compiler is going to know, okay, the user or the programmer has specified a pragma directive. So the program has to create or fork the threads from this point onward, right? So the moment this directive comes, a parallel region is going to be created. So how many threads are going to be created? It depends upon the programmer. So if it has not been told specifically, then whatever the number of cores we have got, those number of threads are going to be created. So if you got octa core, then the 8 number of threads are going to be created at this point of time, right? So all those threads are going to then execute this particular region in parallel. So if we have got 4 threads, then the 4 instances are going to be created, and all those 4 instances are going to be executed in parallel. Fine. And the moment that is end, again the master thread will take the control, and whenever again this parallel section or parallel region comes, the multiple threads are going to be created, or you can say the worker threads are going to be created, right? And after completing their respective job, they are going to be destroyed. So this is the basic execution model of an OpenMP. Fine. Now let us see how exactly the program is being executing. So this is the basic C program, right? Where we have a header file, then we have a main function, and we are just printing a hello message. Fine. And this is how we generally execute our typical C program. So we have a GCC compiler. Thereafter, we have a name of the C program, right? Then we specify the object file, and then we run it, and then we get the outputs and all, right? When we just run the objective file. So this is the basic syntax of a typical C program, and this is how we compile it. So I'm assuming that all of you are familiar in the Linux environment. You are familiar how to write a C program in Linux environment and how generally we execute a basic C program. Fine. Now, let us talk about the hash pragma, which is going to be used very frequently in the upcoming programs and all. So this is nothing but preprocessor directive, which are basically used to give the instruction to the preprocessor, which manipulates the source code before it is compiled. So in C, you would have not the you would have uh, come across the instances where we are including the header files, we are defining the value of pi or if defined. So similarly, we have pragma as well, right? Then the hash pragma directive in C is a compiler specific directive, as stated earlier, that provides a way to give additional instruction to the compiler. So with this, we can give the additional instructions such as that this is a message which has to be displayed, this is the warning which has to be displayed, and this is the error which has to be presented. So these are the things which we can present with the help of this hash pragma directive. Now, hash pragma OMP. So this is the thing which you need to specify at the beginning of each and every OpenMP program. So as stated, hash pragma OMP is a set of directives used in OpenMP, which is open multiprocessing for parallel programming in shared memory system, right? The hash pragma OM directives are used to instruct the compiler to parallelize the certain section of the code, distribute the work among the threads, and it also tell where exactly the threads can synchronize with each other. And of course, it is going to give the control to the other aspects of parallel execution. So it is very important to note that the hash pragma directives are non-standard and compiler specific. So if you are using some Intel compiler, then its behavior may differ. So the point is you have to see whether the whether the OpenMP programs are compatible or not. So it is not like that if you have made a program which is being running fine in GCC compiler, those programs are going to run in other compiler, let's say the Intel compiler, fine. So it is not guaranteed. So they may not be portable across different compilers, and their behavior can vary between the compiler implementations as well. Now we have come to the point where we are just witnessing the first OpenMP program. So this is the typical C program which we have seen just few slides back, and this is the equivalent OpenMP program. So as we can see that earlier it was just having a typical header file stdio, right? And now one more header file have been included, which is include om.h, omp.h. Apart from that, whenever we need to create a parallel region, we need to specify this particular pragma directive over here. So the moment this hash pragma comes into picture, the following section is going to be executed in parallel. So in this case, this particular statement is going to be executed in parallel. Fine. So the thing is printf hello I am thread. So this particular statement is going to be printed by the number of threads. And how many threads are going to be created by default? Anyone? How many threads are going to be created by default? Any participant?
Hello, sir.
Yeah.
Sir, no issue, sir. No request from the participant, sir. You
Yes.
can
So
continue, sir.
yeah. So one of them have said
Sir,
depends upon the number of cores, and many of them are saying two. So the thing, as few slides back we have discussed, it depends upon the system where we are executing these programs. Okay. So as of now, I have not talked about this section. I have not talked about this section as of now. I have just said that let's say this is the piece of code and this is the hash pragma and this is a statement. So I just asked that how many times this particular statement is going to be executed. So it is going to uh, it depends upon that where exactly you are executing this program. So let's say if I'm executing this program in my system, so in my system I have got 6 number of cores. So 6 threads are going to be created and this particular statement is going to be executed 6 times, right? Now let's say this particular thing is being used to compile. So this is the thing which differentiate the typical C program from an OpenMP program. So you must have to take a note of it. So this is the way of compiling a typical C program, and you need to tell to the compiler that you are making the use of parallel programming. Okay, so that's where you need to specifically say to compiler by making the use of this f openmp switch. Okay, so that will tell to compiler that this is the parallel program and number of threads are going to be created and hash pragma are going to be used in this program. So treat this program accordingly. So the name of the compiler, and we are telling compiler that this is an OpenMP program, and then this is the name of the C file, and then this is the object file that is going to be generated after the compilation, right? So if we just execute this thing, then if you have got a quad core system, then 4 threads are going to be created, and if you have got octa core system, then 8 threads are going to be created, and this particular thing is going to be executed that many number of times. Okay, so apart from thereafter, let's say we need to limit the number of threads. I can see someone has got one doubt. So anyway, I'll just explain later on. So till this point, whatever number of cores we have got, there those many threads are going to be created, and this execution will be done. Now let's say we need to limit the number of threads. So if that is the case, then we can make the use of the environment variable. So to do that, we can export this particular environment variable and we can specify the number of threads. So if we are specifying that only 2 threads should be created in this program, then you need to specify 2 over here. So if you run the program thereafter, then only 2 threads are going to be created, because using the environment variable, now you have stated compiler to just maximally create 2 threads only. So this is one thing. And now yes, apart from that, one more thing, that in this function you can see one function om get thread number. So what is going to be done with this function? We are going to get the thread number. So whatever thread is executing this particular statement, that thread ID is going to be printed over here. So if this statement is being executed by thread 0, then its thread ID is going to be printed. Okay. So first time the thread 0 has executed this statement, and the second time the thread 1 has executed this particular statement. Okay. Now this is a student program, but just to visualize, the moment this hash pragma on parallel come into picture, the master thread is forking 2 more threads, right, or 2 threads. So hence the programs are going to be means 2 statements are going to be executed by the created threads. Now let us see a question where we need to write an OpenMP program such that it should add your favorite number, for example 5, to the thread ID and print the result along with the thread ID. But before that, I guess I should show you how exactly those things are being done. So just please allow me a moment. Okay. Yes. So what I have done, I have just installed Windows subsystem for Linux, and in this I have installed the Ubuntu, And now I'm just trying to demonstrate you a basic program. So let's say these are the programs. So let me show you the first program. So this is the basic program which we are talking about, where I have just made use of this OpenMP header file, right? And thereafter, I have specified this parallelism, right? Pragma home parallel. And then I am printing a hello world statement. And at the same time, I am also printing the thread number by utilizing this home get thread number function, right? So what should happen? It must create the number of threads. Depends that how many cores I have got, right? So let's see.
Sir, if possible, maximize the window, sir.
Okay,
Yeah,
but font size.
yeah, that's fine at least.
Is it now? Is it okay now?
Yeah, good.
Okay. So this was the thing, right? As we have discussed in this slide. So we are just creating a parallel region, and then we are printing this statement. So this statement will be executed by each and every created thread. So let us see now. So we need to remember this one, that we need to write F OpenMP whenever we are executing a parallel program. Then let us see the object file as A. So now our program has been compiled successfully, and now let us see the output. So how many threads are there in my system? 6. So that's why that particular statement is being executed 6 times. I got a hexa core system. So that's why the 6 number of threads are there. And now let's say so if I'm limiting the number of threads as 4, now let us try to see the execution. Now as you can see, now the compiler is only allowing 4 threads to be executed. So I hope this thing is clear, right? So that is quite important to understand. Only after that we can understand the upcoming program. So can I assume that till this point each and everything is clear to all the participants? Anyone can respond? Okay. Okay, fine. Thank you. Thank you for responding. So now we were talking about this particular program where we need to write an OpenMP program such that it should add your favorite number, for example 5, to the thread ID and print the result along with the thread ID, right? So these are the hints which we utilize. So rightly I am coming to the program. So that is the program for that. So just to tell you, we have included a basic header file for C, right? And then we have included a header file for the OpenMP program. Fine. Then we are specifying a parallel region from here. Thereafter, we are getting the thread number and storing in this integer variable. Thereafter, to this thread ID, we are adding the stated favorite number, that was 5, right? So whatever number of threads are being created, so each and every thread is going to execute this set of statement, right? So whichever thread is being executing, that thread number is being taken in this integer variable, and then in that thread ID the number 5 is being added, and thereafter we are printing the result. That means what is the thread ID that is being printed over here, and then whatever is the result, that result is being printed over here, right? So that is the typical flow of this program. So at the end, what should come? So this is the output which should come. So given we have got 4 number of threads or 4 number of cores. So in this case, all those 4 cores are being executing in parallel and they are reporting their result. So that means now we have executed our typical parallel program. So I hope that is clear to all. Now let us talk about the threads of execution. So we have already understood that the variety of ways through which we can limit the number of threads, right? So the first way we have studied is using the environment variables. So using number threads, so we can set the number of threads like this, and then we can execute the program. So whatever number of threads you are giving in this environment variable, only those many threads are going to be allowed by the compiler. And now this second way is by making the use of this particular routine within the program. So this is also one of the way through which you can limit the number of threads or you can set the number of threads. So the routine is om_set_num_threads. So let's say we have given 4 to this routine. So maximum threads which are going to be allowed are going to be 4 in this case. Now let's say we have earlier defined the environment variables, and in a program we have also made the use of this particular routine. So in this case, the routines are always going to have the higher priority than the environment variables. So if earlier you have said 2 and in the program you have specified 4, then the 4 threads are going to be utilized to execute this particular program because this particular routine has got the higher priority. Fine. Now let us see another model, which is scope of data variable. So in a program we are going to have number of data variables, right? So now let us see that how that scope is going to be dealt. So how data variables will be shared among different threads of parallel execution. Now let us see that. So consider the scope of data variables are going to be shared. So data objects which are variable can be shared or can be kept private, right? So if we are talking about the shared one, then by default, almost all the variables are going to be shared. That means they are going to be accessible to all the threads and they are going to create a single instance in shared memory. Okay, so let's say we had a main program and initially we just had a master thread and then there came the parallel region. So number of parallel threads have been created. So in this case 4 threads have been created. So if this is the case where all the threads are sharing the single instance, so in this case all the threads will be having the same value. So initially if the master thread has n equals to 2, then all the created threads are also going to have the n equals to 2. So that's what we mean by shared instance. So this is the first thing. And now let's say we do not want that each and every thread should have the value of the master thread. If that is the case, then we are going to set the scope of data variables as a private in that case. So in private, each thread is going to allocate its own private copy of the data and only exists during the execution of a parallel region. And the value of each and every thread means the data variable, the value of each and every data variable at each and every thread is either going to be undefined or 0 upon the entry and exit. So let's say this is the parallel region and at this point of time it is being created. So each and every at each and every thread, the value of the data variable is going to be 0. And let's say in between or in this parallel region, the value of all these thread data variables are being updated and they have now got some value. So whenever this parallel region is being destroyed, then again their corresponding values will become 0. That's what we mean by this enter and exit. So if initially they are 0, then after the intermediate operations or intermediate computation of each and every data variable, let's say over in this case n has been the 4, in this case n has value 10. So whatever value they have achieved in between this parallel region, so on exiting this parallel region, again they are going to have the value 0 only. Okay, so that's what is going to happen when the scope of data variables are going to be defined as private. Am I clear? Now let us talk about one more scope, that is first private. So there can be number of scenarios where we want to keep the value of the forked thread same as the value of master thread. So if the value of the master thread is 2, then we want that each and every thread should also have the same value. Now remember the point. Earlier when we were seeing the first case of the shared one, then each and every thread were sharing a single instance. Now in this case, each and every thread has got their local instance, has got their local memory, and this particular value is being stored in their local memory because they have got their own stake and register. Remember, I told you in the earlier slide. So in the first private, they are going to create their own local copy of the data variable. Fine. So this is what is going to happen in the first private. Okay. Now there is one more thing called as last private. It is also very important because there are a number of instances, number of scenarios where we want to know that which thread at last has executed this parallel region. So we want to retrieve the value from that last executed thread. So if that is the case and that is what is needed in our program, then we can make the use of last private. So what is going to happen in this case? All the forked thread are going to execute their parallel region, and whichever thread is being executed at last, that thread is going to retain its value. Okay, that is the meaning of last private. Am I clear, participants?
It's okay, sir. Sir,
Okay,
it's okay,
okay.
sir.
Yeah, thank you. So let me repeat once again. If we have got 10 number of threads, so we have created a parallel region. It is very much possible that some of the threads are going to finish their job early, and there may be or there is going to be one thread which is going to finish its job at last. So whichever thread is going to finish its job at last, so whatever value that thread is carrying, that is going to be reported with this last private data variable. That's what we mean by it. Okay. Now let us see the work sharing in the form of loops and all. So now we are going to see how the work is going to be distributed among the threads of parallel execution. And the workload should be balanced. For example, each thread should need the same period of time to handle its task, and the iterations of parallel loop are going to be executed in parallel by all the threads of the current team of threads, and the calculation inside an iteration must not depend upon the other iteration. So it is the responsibility of the programmer to make sure that each and every thread or each and every thread is going to get the same sort of workload. Okay, So a schedule determines how iterations are going to be divided among the threads. So that is going to be specified by the programmer in the form of the schedule parameter. Apart from that, the form of the loop has to allow computing the number of iterations prior to the entry into the loop. That means no while loop should be there. Now let us see the scheduling strategies. So these scheduling strategies are going to tell us about the distribution of the iterations which are going to occur in the terms of chunks. Then the chunks may have different sizes. Then the chunks are assigned, or the chunks can be assigned either statically or dynamically. So there are different assignment algorithms, or you can say the type. The first one is static, dynamic, guided, and the last one is runtime. So these are some of the schedule strategies or types, you can say. So we are going to see each one of them one by one. So the first one is static, and in this case the distribution is going to be done at the loop entry time, and then it is going to be based upon how many number of threads we have got and what is the total number of iteration. It is going to be less flexible and almost no scheduling overhead is required, and workload is more or less the same for each and every iteration. And if we talk about the types, then the first type is static without chunk size, and the second is static with chunk size. So let us just try to understand what we exactly mean by these scheduling strategies, right? So let's say again we are going to understand this topic with the help of a program. So the program is, we need to write a parallel C program where the iterations of a loop should schedule statically across the team of threads, and a thread should perform chunk iteration at a time before being scheduled for the next chunk of work. So let's say this is the program which we have just seen in the last slide. So we have defined number of header files, and we have defined number of header files and all, and we have defined the chunk size as 1, and the total number of iterations which we are anticipating in this program is 4. Fine. And this is a typical main function, and in this main function we have declared some data variables, right? And then we have initialized two arrays A and B, right? So this is how we are initializing an array, right? So just basically we have initialized two, and then in the chunk variable we have initialized by chunk size, which we have specified as 1 initially. And in the program, this is the point where the parallel region is being created. Okay, we are just mentioning a condition just to print this thing by the master thread. Of course, the master thread is a thread which is going to have a thread ID 0. Okay, that means only the master thread is going to execute this particular statement, right? So the number of the home get number of threads means the total number of threads are going to be stored in the head thread data variable, and then the number of threads are going to be printed. Okay, then the TID is going to contain the thread number. So we have just made use of this routine to get the thread number, which we have already used in the initial programs, right? Now we are printing this statement that the thread is starting, and then we are making the use of again the hash pragma om for schedule, and in this case the clause is static, and we have specified the chunk size. So which strategy is being used? Static one, and we are also setting the chunk size. Okay, so in this case, what is the chunk size? Chunk size is 1. Over here we have just defined it, right? Yes. Then thereafter we are just adding the elements of the array and then storing their value in another array C, right? And thereafter we are printing the values. So what is the thread ID that is going to be fetched from this particular variable, right? So thread ID is going to be printed. Then the what is the value of the array at 0 index, 1, 2, and so on and so forth are going to be provided with this I. And then what is the value of that respective index is going to be printed with this thing, right? So this is the basic program. Now let's see what is going to happen. Is there any doubt in this program? It's very basic, very simple. Okay, just initialization, and this is the basic things which we have just seen. And in this case, we are executing the for loop up to n number of iteration. And what is the value of n which we have specified in over here? Okay, so this for loop is going to be executed 4 times, means number of iterations are going to be 4. Okay, so this is the number of iterations, and how many number of threads are going to be created, that is going to be depending upon the system which we are using. Okay, so let's say if I am using my system, so I have got 6 threads available with me, so I can make the use of all these 6 threads. If not, then I am going to specify the threads. Of course, I cannot make the use of more than 6 threads because my system only allows to use 6 threads only because of 6 computing cores are there. Now let us try to see what is going to be the output. So for number of iterations having the chunk size of 1 and considering we have got 4 number of threads, or we have set number of threads as 4 in the environment variable. Okay, now that program is going to give us this particular output. So again, those statements are going to be printed at the beginning: thread 1 starting, thread 3 starting, thread 2 starting, thread 0 starting. Okay, like this. From this here, this point, it is going to be printed because number of parallel threads are going to be created, and since we have set 4 threads, so all the 4 threads are going to print this statement. So that's why we are getting this the thread printing a thread starting statement for each and every thread, because we have used this thread ID as well, which is going to be printed, right? Fine. Then as you can see that the addition is being done, and then the result of array C is being displayed, right? So at thread 0, this is the value, at thread 1, this is the value, at thread 3, this is the value, and at thread 2, this is the value, right? And what is the total number of threads? It is 4, which we have just printed over here. And why they are being displayed in a random order? Because although they have been executed in parallel, while displaying, it is the problem of the output output device, and whatever sequence they are getting it from the processor, in that way only it is being displayed. Okay, so it has to be displayed sequentially only. So that's why they are being displayed in a random order. Okay, so now the point which we have to understand is the total number of iteration were 4 and the chunk size was 1 and the total number of threads were 4. That means each and every thread is executing one iteration. So we had 4 threads, so each and every thread is executing one iteration. So one is here, one is here, one is here, and one is here. Okay, chunk size means how many iteration a thread should execute. So if the chunk size is 1, that means we are assigning only one iteration to each and every thread. That is the very important point which you must have to remember. Okay, now consider a scenario where we have got the number of iterations as 4 and the chunk size as 2 and the number of threads same, that is 4. So now we have increased the chunk size. That means each and every thread is now going to execute 2 iterations. Earlier they were just executing one iteration. Now we have set chunk size as 2. Okay. So now let us see what is the output. Now, as you can see, even the thread number 0 is executing 2 iterations. And when it is done with 2 iterations, the next thread is also executing 2 iterations. And what was the total number of iterations? 4 only. So only 2 threads were sufficient to execute all the 4 iterations. Am I clear, participants?
Sir, sorry for the interruption, sir. It's okay, sir. Few questions are there from the participants, sir.
Okay, so should I proceed?
Sir, where we have to declare the number of threads?
Where we have to declare. See, if we are not declaring, then by default, whatever number of cores are there in a system, those many threads are going to be created. So let's say I have got 6 number of threads. So in this program only, you can set the number of threads the way we have declared in the earlier program, or you can set the environment variables which we have discussed earlier, like this.
Yeah, it's fine, sir. Sir, and one more question, sir, from
Over here.
Dr. D. Kishore Babu, sir. Is there any priorities for scheduling, sir? This is one more question.
Yeah, priority. See, in the parallel execution, we have the variety of strategies. For example, static, dynamic, and guided. So guided means now it is up to the programmer. Okay, so as of now, I have just discussed, or I'm just discussing the first one only.
Okay, sir. Thank you, sir.
Okay.
Thank you, sir.
Yeah. Thank you. Why it is very important? Because if you don't understand these things, then it is going to be very difficult to understand the coming concepts and all. So that is why I'm trying to explain these things in as much details as possible. Can we do execute in GCC compiler? Yes, you can execute this one. Okay, you can very much execute this program. So the slides are going to provide to all the participants. You can just copy this program and you can execute it. So how one can execute that, I have already stated. I am already running out of time because I have got only 1.5 an hour and a lot of
Sir.
contents are going to be there.
Sir, sorry for the interruption, sir. And one more question from Deepti ma'am.
Yeah.
Can we do execution in GCC compiler?
Yes, so that's what I just said. We can very much execute this program in GCC compiler. So I have just shown the execution in the GCC compiler only, this one only.
Oh,
So this is compiler only. This one, no? I have just shown, no?
yeah.
Yeah, this is compiler only.
Okay, sir. Fine, sir.
So I guess now you would have realized that what is going to happen when we have got these scenarios. Okay, so I'm assuming that I have got more number of codes. So in my case, I've got 6 number of codes, so I can accommodate 4 threads at any time, right? So that is going to happen. Now let's suppose another scenario where we have got 4 number of iterations, and now this time I have set the chunk size as 4, right?
Sir, and
So
sir, sorry for the interruption, sir. And one more question, sir, from HOD CSM, sir. What happened other 2 threads if you declared 4 thread chunks are 2?
yeah, so I'm covering all the scenarios, all the possible scenarios. So I'm damn sure if these scenarios are understood, then you will understand what is going to happen. Okay, so 2 I already discussed these 2 scenario, and now I am going to discuss the third scenario, where what I have considered the number of iterations are same, that is 4, and now the chunk size have been set as 4, right? And the number of threads are going to be kept same, which is 4. So chunk size is going to state us how many iteration is going to be executed by a thread. Since we have said that the chunk size is 4, that means each and every thread has to execute 4 iterations. So in this case, when the thread are going to be created, only the thread 0 will find that it is sufficient for itself to execute all the 4 iterations itself. So that's why all the remaining 3 threads are not coming into picture. Only thread 0 will execute all the 4 iterations. Right? And now consider one more scenario where the number of iterations are 8. And now the chunk size is 2 and the number of threads are 4. So if we just try to visualize this scenario, then what is going to happen? Each and every thread is going to execute 2 iterations. Right? So in total there were 8 iterations. So each and every thread is going to now execute 2 iterations because the chunk size is 2 and total number of iterations we had were 8. Okay, so there are a number of things. Let's say if the number of iterations are 10, then what is going to happen? So after this 8, again the 2 threads are going to be executed by thread 0 only. Okay, so on so forth. You can just visualize, and if not, then you can have the program. You can just play around these number of threads and all by the program. So believe me, when we were being trained on this one, we took the whole day. So it's quite tricky, but I'm trying so that you can at least get the practical experience of these programs, which is very important to visualize how actually parallel programming or the OpenMP function, because in the coming sessions you are going to have the MPI sessions and all, or the Open SEC things and all. So that is quite important. Now we are going to see what is going to happen in the dynamic scheduling. So in this case, all the things are going to be, means the number of iterations which are going to be executed by the threads are going to be assigned dynamically. Okay, so now let us try to understand this thing again with the help of example. So this time the only change is that the schedule has become dynamic instead of static, right? Now, if we execute the program with dynamic strategy with the number of iterations 4 and chunk size 1 and the number of threads as 4. Now look carefully at the output. What is happening? So as you can see now, the thread 0 has got its role to play. Okay. Thread 3 is also playing a role. Thread 1 is also playing a role. And thread 3 is also playing a role. Right? But the thing is, which you can just understand, that thread 3 has been executed twice, right? And thread 2 is missing. So in this case, what is happening? Thread 3 has finished its job early, and when the compiler found that the thread 3 is free, at the same time thread 2 was free, so dynamically thread 3 has been given the job to execute that particular iteration. So dynamically it is going to be stated that which thread is being given the responsibility. Okay, so that is the difference in between the static and dynamic. So let's say we have got 100 number of iterations and we have got or let's say we have got 50 number of iterations and total number of threads which we have got are 4. So initially what is going to happen, that each and every thread is going to execute the 10 number of iterations. So what will be the leftover iterations? That is going to be 10. So when the compiler is assess or is going to assess that okay, 10 iterations were given to each and every thread. Now what is the solution? So whoever have free earlier, accordingly the number of iterations are going to be assigned. Okay, so whichever have finished its job early, so accordingly the number of iterations are going to be assigned to that particular thread by the compiler. Okay, so that's where the dynamic scheduling is going to come into picture. And while in the case of guided, it is going to be depending upon the user how exactly that is going to be defined. So what is going to be the initial chunk size, then what is going to be the default one, okay, oh sorry, what is going to be the minimum one, okay, and when the execution speed is going to increase and decrease, all those things are going to be specified by the user. So that's why it is going to be it is being called as guided. And in case of runtime, using the runtime environment variables, we are going to define the type of the strategy and the chunk size. So that's why it is being called as runtime. So with the using the environment variables, we are going to set the scheduling type and the chunk size. Okay, so that's what is going to happen in the runtime scheduling.
Rajesh sir, sorry for the interruption, sir. And one question from the participant, sir. Durga Pallavi ma'am.
Yeah.
What is the relationship between chunk size and threads?
Threads we are going to execute, and the chunk, that how many iteration a thread should execute, because we as a programmer are going to devise the strategies that how many iteration a thread should execute. Okay, what is a thread? As stated earlier, because we are assuming that we have got a HPC system. HPC system is we have got many number of cores, right? And each and every core should be utilized. So let's say if I have got 4 number of cores, then at max I can create 4 threads, right? So each and every thread can do some job. So now let's suppose you have got a program, and in a program you have got a for loop, and in that for loop you have got a number of iterations, let's say 1 million, right? If you got 1 million iterations to execute, then how you are making sure that each and every thread is being utilized in a proper way? So that's where the scheduling strategies are going to come into picture. So if you are specifying, then good. If you are not, then the default settings are going to come into picture. Okay, so in default setting, the chunk size is going to be 1, means each and every thread is going to execute one thread at a time. And let's say if you have increased chunk size, then accordingly those set of iterations are going to be executed by the created threads. So if you set the chunk size as 10, then the thread 1, sorry, thread 0 is going to execute 10 iterations first. Then the turn of thread 2 will, or thread 1 will come into picture. So that's what we mean by the chunk size and the threads. So when you are going to write the programs, when you are going to visualize these things, then it will be much more clear to you. Okay?
Thank you, sir.
Yeah, thank you. So now the work sharing sections. So we can make the parallel sections as well. So this is how first you need to specify the clause and all. Sorry. So first you need to specify this section clause, and then this will allow you to create the parallel sections. Okay. So these in this program we have created 2 parallel sections. So that means these 2 parallel sections can be executed by 2 different threads. Okay, that's what it means. So in this section we can have number of statements and all. So it is useful when, especially when we have got number of functions, so the routines and all, and when those routines have to be executed in parallel. So that's where these sections will come into picture. So in this program we are calculating a table of 2 in the first section and a table 4 in the second section. So number of threads are being utilized, but all those threads are being executed, or rather these sections are being executed in parallel. So hence you can see the result. Okay, so more or less over here both these sections are being executed in parallel. Then this is another important concept, that is synchronization, and we need to understand this one. and it is going to come where we have got the shared data variables, because in the parallel program this is very important. So what is the thing over here? The thing is, we need to see how exactly we deal with the race condition. And what is the race condition? When more than one thread try to update the shared data variable. So that is called as a race condition. So consider a program where we are just trying to print the sum of first 10 numbers, right? So we have just declared some header files for OpenMP, and then we have set the number of iterations, right? Then we have initialized the array, and we have declared some data variables, and then we have created a parallel region to find this value. Okay. So what is going to be happen over here? Number of parallel threads are going to be created, right? And each and every thread is going to execute an iteration, right? And finally, all the iterations are going to be executed. How many iterations? 10 iterations, because we need to find the sum of first 10 numbers, right? So this is the basic logic. This is how we find out the sum of 10 numbers, right? And then at last we are printing the sum. So what should be the output? Output should be like this. So the output has been executed multiple times. So what should be the output? Output should be 45, sum of first 10 numbers. So when the program has been executed first, it was saying the result as 29. Second time it was saying the result is 21. And then 45, 45, 43. That means the result is not consistent. And why? It is because that the variable was being shared by the number of threads in parallel, and when one thread was dealing with one variable, please listen carefully, when one thread was dealing, or let's say reading the current value of a data variable, at the same time another thread has come and read the value of that data variable. So before the first thread who read the value of the variable, so that value was not updated, and the second thread has read the value. So that's what will happen. The conflict in between the threads will be there. So randomly they will be updating the values. So that's why this inconsistency is being reported. So let me repeat. So let's consider a scenario where we have got two threads. Okay. So let's consider one thread has just read the value. Okay. To update this variable. Fine. At the same time, another thread has come into picture, and before this particular thread updated this value, another thread had just read its value. Okay. Now what happens? This thread T0 now calculated the value and submitted its value, right? But the point is T1 has read this value only, and now it is submitting this value. So the inconsistency will arise. Okay. So that's where the problem comes, and that's where these inconsistencies are being coming. So this is called as race condition, and to ensure that what can be done, we can declare a critical section. That means if there are number of threads which are being executed in parallel and there comes a critical section, then it has to be declared as a critical, so that only one thread at a time can access this region. Okay. So to ensure that this particular statement has to be used, and that is hash pragma on critical. So with this, if you have specified the critical region and the same program is being executed, then you will find that no inconsistency is there. Okay, and with this, the problem is if you are going to make the critical region, then more or less after parallel computation, at this point, the program is going to behave almost sequentially. So that is the problem. So to make it efficient, some other better solutions are there, and that is the make the use of critical. So as stated earlier, each and every thread has got their own stake in register. So they can create their local sum, and at the end they can finally calculate the final value. So with this, what will happen? All the intermediate overhead is going to be looked after this system only or by the compiler only. Okay, that how the intermediate sum is being calculated and then how the final sum is going to be calculated. So all these overheads are going to be managed by the compiler only. So that's where the efficiency is going to come. So now in order to understand what is going to be the performance difference, so let's consider where we have got the number of iterations as 1 million. Okay. Yeah. So this is the thing when we have used the critical section only. So this is the time we have just made the use of this time. Okay. So this was the time which was being taken to execute these many number of threads. And when we made the use of critical section, at that time you can find the efficiency. Right? So that's what difference we are going to observe. Remember, we make the use of parallel programs for the science and engineering applications which have got huge computational requirement. Okay, so even the computations do run for the months and years and all. So these small things are very important in writing up parallel programs. And then we have got another solution for the same thing where we make the use of atomic. So this will also give you much more optimization, which will give you the better result than the critical. Okay, critical is just way of writing the sorry. Yeah, atomic gives you the better way of dealing the same thing. And apart from that, we have got one more thing called as reduction, and it is also a very important thing where the same thing, because in parallel programs there are number of situations where we need to reduce or where we need to execute the programs like this for certain operations. So what can be done? We can just make the use of this reduction operator along with some clauses. So let's say, yeah. So if we just make the use of reduction clause, so over here, what is being done, that we need to have the reduction over the operator plus, which is this one, and over the variable s. Okay. So with this, what is going to happen? The reduction is going to be done. So it is also going to report the same value, and these are the data types and the operators and their respective initial values which are going to be there with the reduction operator. So you can just go with this to understand the things, and we can set the barriers in the form of number of things. Okay, since I'm running out of time, so I cannot discuss many things. So anyway, these things have been kept. You can just see what is the key difference in between the critical, atomic, and reduction. And now one more thing, that is Slurm, and Slurm is the way through which we submit the job to the HP system. So whatever thing we have got, we can submit using this Slurm script. So it is nothing but a sort of shell script where you specify what is the number of nodes, that how many number of nodes you required, then per node how many number of tasks you want to have, then for how much time you want to submit your job, then what is the total time which you are trying to get from the SPS system, then what sort of node you would like to have, and then at the end you will be getting the output file, and if in case there are some error, then you are going to get those errors in this j.out error file as well. Okay, So this is how shell script or the Slurm script look like. You after the completion of the job, you are also going to get the email notification and to whom and means for what notifications you want to have the email. For example, the job has started, ended, fail, all. So this is how this Slurm script looks like, and this is how you can tell it. And of course, what specific modules you want to utilize to execute that thing, you can specify over here. And these are some options which you can make which you can utilize with the Slurm script. And as control is a command which can be used to have the other administrative things. For example, how many partitions are there and how many nodes are being used, what is the state of the job, what is the schedule and all the things. Okay, what is the resolutions and all. So all these are the things, and these are the short code which is going to be written by the Slurm script after the execution. So these are the common cases where we make the use of Slurm script more often. So with this, I guess I'm running out of time, so I should end my session here only. So let me know if there are some questions, please. Any question from the audience? Any question? Am I audible?
Yes, sir, you are audible.
Okay.
So let me check in chat box the new questions. Sir, I think you parallelly addressed the questions. Thank you very much.
Okay.
Yeah.
So
Just a moment, sir.
yes, sure, I'll share the PPT. Okay. So with this, I guess. So once again, thank you so much for having me here in this FDP. It was a pleasure for me to be here. So with this, I'll just end my session here only. Thank you.
Thank you very much, sir. Good evening, everyone. Thank you very much. I am really privileged to flash once again the insights of the session. As we have just concluded an excellent and enlightening session on introduction to OpenMP, and we also touched upon the different topics and the distinguished lecture, the session delivered by Dr. Rajesh Doriya sir from NIT Raipur. So it has been a privilege to, it's a privilege for all of us to have him as a speaker today, and provided an interactive session on OpenMP. So this is, we all know this is basically a capsule for the parallel programming landscape. So sir not only just touched upon the basics, but he has extensively provided the knowledge on the way how the resources can be used for the parallel programming, including compiler directives and shared architecture and multi-core environment, and how threads can be used to handle the multi-programming. Sir, your session really enlightened us, sir. I know you are capable to take a day-long sessions, and definitely we would like to have more interactive sessions in future, sir. Thank you very much for accepting our invitation and spending your valuable time and quality content with all the participants. So once again, on behalf of the Department of IT, Chaitanya Bharati Institute of Technology, on behalf of our principal, our head of the department, and our staff, and particularly on behalf of the all the participants who are the beneficiary of the today's enlightened session, I extend my sincere gratitude to you, sir. So really, we enjoyed the session, sir. And this, winter evening, so your session made us to really think of parallel programming. So thank you very much, sir.
Thank you, Ramkrishna sir and Satyanarayana sir for having me here. Thank you once again.
Thank you, sir. So, dear participants, we'll have a 5 minutes of break for the next session. And then meanwhile, I request all the participants to please give your feedback through the Google form shared in the chat box. And after 5 minutes, we'll have another session which is having a hands-on on OpenMP.